Okay, so now we're going to derive the Michaelis-Menten equation, and this is simply a way to get the rate of a reaction as a function of the substrate concentration and a constant that is specific to the individual enzyme substrate interaction. Uh, at the end of the day, we should see something that looks very familiar with a formula we're already used to, which is our fractional saturation binding formula. And so we're going to just start with the actual reaction. E plus S goes to enzyme substrate complex. And then this is actually two reactions. So this is one, this is two. And then you have ES goes to E plus P, right? So remember, the reaction ultimately that we're interested in is S goes to P. And the delta G of that reaction is unchanged by the interaction of that enzyme, and the enzyme must be unchanged when all is said and done. And so here you're starting with E here, you're starting with, you're ending up with E over there. So the enzyme comes out exactly the same. The substrate concentration is a temporary kind of thing. So most of the time, we write this all out as one formula. E plus S goes to ES, which goes to E plus P. And then this will occur at a forward rate of K1 for the E plus S goes to ES. And then it will break down at a rate of K minus 1. And then here, the ES complex will break down at a rate of K2. And then it will form at a rate of K minus 2. Um, So this forms kind of the foundation of everything that we're going to be doing here. And I will say, for the record, that I haven't memorized this derivation. I never memorize it. I'd probably struggle actually to give you the Michaelis-Menten equation off the top of my head, but I know how to go through the process. And so this will take us through the rest of biochemistry. If you understand the logic of these processes, then you can get through without kind of going for straight memorization. And it's kind of like riding a bicycle. You will see when you have this in medical school or graduate school or whenever that you will get it and you will understand it in a way that your colleagues won't because all they did was memorize a bunch of letters for the exam. So I would say go through the process and you should be good. Now, in order for us to really kind of derive this equation, then we need to make a couple of assumptions, some of which we already talked about. So the first is that we make what's called the steady state assumption, which, as we said last lecture, is simply that the ES formation is equal to the breakdown of the enzyme substrate complex. Um, uh, the second is this, that we can define a total enzyme concentration that is equal to the amount of enzyme that's free plus the amount of enzyme that is bound in complex. That makes sense, right? E, E total is equal to what isn't bound plus what is bound. And again, we saw something similar to this in the protein ligand binding equation. And so we can define here just by using algebra, we can say that the free enzyme is equal to the total enzyme minus the enzyme that's bound in complex. Okay, and that's something that'll come up useful later on. So let's see, this is 1, this is 2. The other thing that's kind of useful is this. We will say in general, the substrate concentration is much, much greater than the enzyme concentration. So we can make another assumption, which is that we don't have to do the same analysis in 2 for substrate concentration. So we can say the total substrate concentration is equal to the free substrate plus the amount of substrate that's bound in enzyme, and that all of that is basically equal to free. Or to put another way, the amount of substrate that's bound in enzyme at any given time is negligible relative to the amount of free substrate. And that just allows us not to have to deal with the amount of substrate that's in enzyme at any given that's bound to enzyme at any given point. Okay, those are our three assumptions that we make. And oh, well, one more. Let's just go and simplify our equation a little bit here to say E free plus S to K1, K minus 1, ES. Now we're going to limit our view to initial time points. And so at the initial time point, product formation is negligible. So there is no product, right? And so that means if there's no product, there's no way for the reverse reaction from E ple to ES to to go through. So here we can simplify our enzyme equation such that it is E free plus S goes to ES goes to E plus P, and there's no reverse reaction. All right, so those are the assumptions. So this is what we're all going to start with here. So let me flip to the next page, and then we can go work with that. And we're just going to manipulate this in order to determine the rate of reaction as a function of substrate concentration. E ple, K1, reverse, K minus 1, ES, K2, E plus P. All right. So here we go. Now, we are looking at the rate of product formation, right? And we know if we just break this reaction up, ES, K2, E plus P, we know that the rate of product formation is equal to what? V0 is equal to the is a function of the substrate concentration, right? In this case, the substrate is ES. So V0 is equal to K2 ES, right? Ultimately, this is all we're trying to get to, is to figure out this expression. V0 is equal to K2 ES, right? The problem is we don't know what ES is, right? ES is something that's formed transiently over the course of the reaction. And so we need to figure out a way to determine the concentration of ES at steady state. And so everything that we're going to do now is to look at how do we figure out what the concentration of ES is at steady state. And remember, we make the steady state assumption, which is to say that the ES, the constant ES formation, is equal to the rate of breakdown while these guys are at steady state. And so we're going to use this now. Now, if we could figure out what the enzyme substrate concentration is, we can set them equal to each other, and then we can solve for ES. And that's all we do in the Michaelis-Menten equation. And so this is the way I do it. There are lots of ways to do it. You know, you do it however makes you happy. If you go up on some of the other kind of sites, they might have a different way to do it, but it's all the same algebra. What I do is first list all the ways that ES can form and all the ways that ES can be broken down. And so here, enzyme substrate formation, How does that happen? Well, let's see. This is the equation. Let me change colors here. This is the equation, right? The way to get to ES is only one way, right? It is what? The K1 times the substrate concentrations. So formation would be equal to K1 times E free times S, right? There's no other way to form the enzyme substrate complex because we aren't looking at the reverse reaction coming from enzyme plus product. Now, if you look at the rate of ES breakdown, it can occur in two ways, right? We can break down ES by going forward to product, right? And that would be equal to K2 times the enzyme substrate complex, right? And the other way to break it down is to go back to the enzyme and substrate, right? So here you can break down ES by going in the reverse direction, and you can break it down going forward. So this would be plus K minus 1 times what? ES, right? Which is the substrate in in the reverse reaction. So here, this reaction would simply be ES goes K minus 1 to E plus S. Okay, and so that's it. These are the two ways in which you can break down ES and form ES. There are a couple of things here. We don't know what the free ES concentration is, right? And so we have to say we know that we can say that uh, the free enzyme concentration is equal to the total enzyme concentration minus the amount of enzyme that's in substrate. And this is times S, right? And just to do, a little bit of algebra here and distribution, we can say K1, and I'm just moving this over S. Just remember from algebra, we have to distribute these guys, right? So we're distributing here. So K1S E total minus K1S ES. Boom, right? And then this has to be equal to K2 ES plus K minus 1 ES. All right, so this is a long expression, but fortunately the algebra is fairly easy here. Remember, what we're trying to get to is this, a way to express ES so that we can get to the reaction rate. So all we have to do now is solve for ES. Y'all, there's all sorts of ways to do this. I know some people go ahead and define Km here, but I like to wait till the end. This is just kind of whatever floats your boat, really, in this case. But what I do is move ES to one side of the equation. So here, plus K1S ES plus K1S ES. And so this whole thing would be equal to K1S times E total is equal to K2 ES plus K minus 1 ES plus K1S ES. And then you can factor out the ES here. So this would be K2 plus K minus 1 plus K1S all times ES, right? And then all you have to do is divide by K plus 2, K minus 1 plus K1S. And there, I'm going to flip these things around. Here you have ES is equal to K1S E total over K2 plus K minus 1 plus K1S. Okay. Yeah, and so this is it. We just solved for ES. Congratulations, guys. The only thing now to do is just simplify this a little bit. One, all these Ks are constant, and so we can move them all and kind of lump them all together to form a new constant, right? And so we do that simply by dividing by K1. So here, take K1 divided by K1, S E total over K2 divided by K1 plus K minus 1 divided by K1 plus K1S divided by K1. And then you can cancel these, cancel these. This you can add, oops, I'm running low here. And so this becomes K2 plus K minus 1 over K1, which we can define as a new constant, which we call Km. And so Km is simply this combination of K1, K minus 1 over K1. So if we do that, then this equation becomes ES is equal to substrate concentration times the enzyme, total enzyme concentration over the Km plus the substrate concentration. I'm just gonna highlight this guy. Boom. All right. So we just solved for the enzyme substrate concentration, but remember the rate of reaction, V0, is equal to K2 times the enzyme substrate concentration. And so now we replace this expression with this one. So V0 is equal to K2 times S E total over Km plus S. So this is the Michaelis-Menten equation. There's a little bit of cleanup left here, but this is basically it. Now we have the reaction rate as a function of substrate concentration and enzyme concentration. So I'm running out of batteries, so I have to finish this up quickly, but in time. So now the only thing we're going to do is kind of do a thought exercise and say, hey, if all of your enzyme is in complex, so if you use 100% of the enzyme, then you have no free enzyme, so you must be operating at the maximum possible velocity. So we can define a Vmax that assumes that 100% of the enzyme is in complex formation, and that would be equal to K2 times E total. All right. And so there, if we say Vmax is equal to K2 times E tot, and V0 becomes Vmax S over Km plus S. Boom. That is, I believe, the Michaelis-Menten equation. Is it? Shoot, I don't know. Oh, yeah, how about that? It is. Okay, so now what have we done? We have expressed the reaction rate as a constant that is a function of the actual reaction between the enzyme and the substrate, another constant that is a function of the total reaction rate, um, and then substrate concentration. Now, remember, what did the ligand binding, the fraction of saturation equation look like? Theta was equal to what? L over what? Kd plus L, right? So it looks very similar to our original fractional saturation binding, except now we have an expression that factors in the catalytic activity of the enzyme. Whew, that was a lot, but here we are. We have just derived the Michaelis-Menten equation. And I will say this, um, do not just kind of repeatedly look at this on videos and think you got it. Go ahead and try this derivation. I think we'll do this in class, but go through and make sure that you understand the steps and how they go through on your own. I'm down to 3%, so I have to end. It's been real. We'll chop it up and talk about this this week in class. Peace.